Okay. Farus, you say you missed the first 5 minutes of class. Can you briefly explain where we would encounter this shape? When you say encounter this shape, is it this shape, Farus? Farus, I know you got no mic. Okay, can you tell me how we get this shape? Is that yes? Okay, so this shape, okay, is based on mathematically and is derived from Tresca's equation, okay, which I'm not going to derive. So I want you to observe this is the output and those are the conditions. Are we clear? 5 rules. Okay, it's a mathematical expression. Okay, good. Right. I know online you have to have mic to speak, unfortunately. Okay. All right. Now this is what engineers like yourself should be doing. Okay. This question. Okay. And this question has a lot of layers. And not, if you go to a company, not all engineers will know the different layers, okay, for this analysis. But Max Master Gadget has to know, okay. So this question is very similar to one of my expert witness condition that I have to testify, okay. So I'm not give too much background, but the calculation is done by 3 engineers and checked by 1 principal engineers, okay. And there's something that they got it wrong. So that's why I brought this question up. I realized that this is very similar, and I think this is critical that you all have to know, okay. Right. So for this case, we are going to combine everything that we have learned, okay. So what do I mean by combine everything that we have learned? Okay, so we are going to do, okay, before we go on, let me show you what's the problem first. So the internal loading at a critical section along the steel shaft of a ship are calculated to be a torque of 2,500 pound-inch. So we have a torque. Don't worry about the torque. Don't worry. I will show you the formula. It's real easy. Okay. So I know we have not learned torque, but nothing to panic about. It has a bending moment of 1,500 pound-feet moment, and it has an axle load of 2,500 pounds. Okay. Now, given if the yield point is 100 ksi, right, and you have a yield in shear of 400 ksi, determine the required diameter of the shaft using the maximum shear stress criteria. So now it comes to your mind, maximum shear stress. Now you know it is what? Tresca, right? Because it declared maximum shear size. So you know that. So we're going to apply Tresca criteria. So what do we mean by we have to apply Tresca criteria, right? Like what we have written before. Okay, like what we have written before, right? These are Tresca's criteria, okay, of mathematical expression, where stress Y must be equal to stress A minus stress B, the shearing stress, okay. Now this is material behavior, stress U divided by 2. This is calculated. You have to confirm with the what? With the calculated, or not you are in a big doodah, okay. So 2 conditions that we have to meet now, okay. So I'll write down here. So one of the conditions that we have to ensure, okay, we have to apply Tresca. We have to ensure, right, we have to ensure that stress U, right, must be equal to stress A minus stress B, right, and right, tau max must be equal to stress max minus by stress mean divided by 2. Okay, we have to ensure that. Okay, then we also have to check with 3D mold circle to determine the largest diameter of the circle, or largest diameter. Okay, so now you have to apply 3D mold circle, 3D world, 3D material property. Okay, how they are tested in real life. Okay, right? So from here, before we start anything, we're going to call our transformation. Okay, so this is our X, this is our Y, okay, this is our Z. Okay, so that's our X, Y, Z. Right, so let's see what stress contribute to what. Okay, let's see what stresses contribute to what. So I'm going to do a very short refreshing formula. Okay, so we know that the bending moment, or we're going to look at normal stresses. Okay, we're going to look at normal stresses. Okay, so normal stresses, right, induced by axial loading and bending moment. So I'm just going to write out the general formula. Okay, so stress X is equal to P over A, right, plus by M Y over I, right? This is our axial, this is induced the normal stresses. Okay, then we have shearing. So normal stress is just axial loading and bending moment. Shearing stress, we have two. Now we guys say, oh, not again shearing stress. Okay, so shearing stress okay, they are induced. The first one is induced by shear force, right? So shear force is equal to, now you guys know, right? The shear stress is equal to VQ over IT. Okay. And then the other one is induced by torque, which is capital T, right? Whereas this is V, right? So the shear stress now it's just a formula. Okay, this class by right I should teach you torque, but I did not have time. Okay, but it's just one key formula that you have to know. But the shear stress is equal to TR over J. Okay, TR over J. So if we look at TR over J, right, I'm going to tell you what they are, right? So T, as you know, is the torque. So it's in Newton meter, or it can be in pound inch. Okay. The R is the radius of the shaft. Okay. Of the shaft. So this is in meters or inches. And the J is the polar moment of area, or polar second moment of area, where this is in meter 4 or inches to power 4. Okay. So where J, I'll write down the formula for you guys. Okay, J. Okay, you will need this to apply. Is equal to I. Okay, and J is equal to pi over 2 bracket radius to power 4. Okay, so this is for solid, and for hollow, radius on the outside minus by radius on the inside, power 4. This is for hollow shell. Okay, so all these formula except the last one, you have seen it before. Okay, now I'm going to draw. Okay, I'm going to draw the stress distribution. Okay, I'm going to sketch the stress distribution now. Okay, for the normal stresses and for the shearing stress. Okay, and this is how it will look like. Okay, so you guys know so this week's topic is nothing new except Tresca and the torque equation. Now it's about integration. Everything you have learned from week 1 to now. Okay. So I'm going to, so if you look at this, okay, so this is for normal stress. And we're going to combine with Mohs circle, okay. So this is your normal stress. This is your y distance, okay. So for this case, you know that the distribution, right? Some of or most of you will remember how this is distributed. So you have, I know this is eccentric loading, okay? That's the general trend. You will have a stress state doing this, right? So at a centroid, so this is the position of the centroid, right? The normal stress is equal to 0, okay? And then I'm going to draw those induced by the shear force. Okay, so this is your shear stress now. Okay, this is your y distance, and we know that we are going to get a distribution, right? So we have a distribution like this, and this is very opposite in this different from normal stress distribution, because at the centroid is where maximum shear occur, right? You say, oh, right? And when I was a young engineer, I was not taught like this. This is when I discovered, maybe when I was doing my PhD. Okay, I thought, but okay, if the normal stress is higher, just use the normal stress. Okay, my shear stress, I don't know what is it, don't know how to incorporate them. Okay, I just put a safety factor of 2.0. We're good to go. Okay, we have to be careful with that. Okay, maybe sometimes your 2 is not enough. Your factor of safety of 2 is not enough. Okay, we have to be really cautious in situation like this. Okay, and then the torque distribution. All right, the torque distribution will look like this. All right. Some of you will say the real world is not easy. You're absolutely right. Okay. So in terms of radius now, okay. So if you look at the expression over here, is a function of radius, yes or no? Right, it's a function of radius. J is constant, torque is constant, the radius changes, right? So the distribution will look like this. Right, the distribution will look like this. So the bigger the radius, The bigger the better. Eugene, seriously, what's wrong with you today? Yeah, I won't post the wrong address until Jenna told me today. Like, it's the wrong. I mean, she did not know it's the wrong address, but she told me I checked it's the wrong address. Right. So this is the distribution for the shear. Now this is due